So here I am making videos again, and this one's about opal. This is a piece of wood opal from Banten, Indonesia. Look how white that stuff is there, huh? That's pretty incredible. And there's play of color in it. It's got reds and stuff. But it's actually black opal. That stuff's white. And there's some blue play of color and red play of color. Play of color is not color inside the stone. It's like a rainbow kind of, with the light breaking inside the stone because of the structure of the stone. It's kind of like drops in a rainbow, drops of water, and make rainbows. And so that's what you see here. And the opal itself is dark because it absorbs light, not because there's a black pigment inside. Now, the wood itself has stuff like iron pyrite in it, and it's black. The wood itself is black from those sulfides in the environment. The opal is black because it's made out of something that's a neutron shy of stability, and so it absorbs light. Like carbon-13 is what diamonds are made out of. Carbon-12 is what people are made out of, and you can burn them up, and people and trees and, grass and all that other stuff. This wood, right? Wood. It's carbon. Wood. Hydrocarbons, and the other stuff goes away and the carbon stays. Now it's replaced. The stuff that goes away over time is replaced with AUPT dust. Really, really fine, like molecular fine AUPT dust. And it gets in there. And if it's half the size of a wavelength of visible light, in subsequent volcanic activity, and during the KT extinction event, there were several rounds of planet-wide, like all around the planet, volcanism for thousands of years, and it left hundreds of meters of radioactive volcanic ash all over the Earth. That was what caused the extinction to be so thorough, because the radioactive volcanic ash literally covered the Earth. Very few things survived. Redwood trees on the west side of Mount Whitney, probably in valleys and stuff in the mountains that were standing at the time, but who knows where those mountains are now. But that's where life came from, and from existing life that came before the KT extinction event. And it was not dinosaurs, it was people like you and me, because they left things in the rocks with messages. If you're going to send a message through time, what you want is something that's not going to go away, right? It's not going to rust or deteriorate. So they sent them in the rocks with AUPT. Um, and I have rocks that show a whole story of the KT extinction event. And it was an act of war. We lost. And that big ship sticking out of New Mexico was ours. It's not like an alien spacecraft. We were perfectly capable of flying through the stars at the time. And I think it was about 100,000 years ago, and there's been maybe 3 bouts of planet-wide volcanism since then. The Dine tell us this, that they entered this, the 4th world, through a straw or reed from deep underground. And that ship has the very highest point, a little hamlet called Tohachi. I think that's where they come out. And go back in, right? When things get bad, like for instance, global warming is about to cause a major flood. Kind of like Noah, right? And here I am, working away, and telling y'all that if we don't stop using petroleum oil, the polar ice is going to melt. And it's not like speculation, it's physics, right? I don't think it's going to happen. I know it's going to happen because I saw 2 other climate change models before I even did my own, right? And when I did my own research and did my own programming and used things I know. And they all 3, the first few were way back, man. I read them when I think when I was when I first started back to school in '93. Maybe a little before that, maybe even '89. And then in '94, I bought my first computer, my first real computer, a 386 with Windows 3 on it. You had to boot through DOS. And I was playing with the Unix version of PCs, Linux, and developing Fortran programs to do climate models. C and C++ as I was learning those, and then I started working with Fortran 77, the object-oriented Fortran. Yeah, this is almost 30 years ago now. It was a long time ago. And I learned some of the older languages like Fortran for scientific purposes. So Fortran was the language of the scientific community in computer programming at the time. And so my learning of object-oriented programming involved the climate change models, and you have to model each separate system as a different function, and so object-oriented programming works real well for that. And you can call it from different you can call those functions from other functions, right? So you can say, well, the sun's currently we're at solar minimum here in the north, but the south is at solar maximum. And so you can call those kind of functions, and it does if then else's, and figures out where you need to go and calls other functions, and they feed back on each other, just like the real world does, or at least that's how I tried to model it so that I could watch. Because what regulates temperatures on planet Earth is the Pacific Ocean, right? The Pacific Ocean takes up half the planet. If you look on Google Earth, there's almost a straight line along the west coast of the United States that goes down the east coast of Eurasia and down into Australia and to Antarctica and all the way back up South America to North America in almost a straight line. And so half of the planet is the Pacific Ocean. And that is the major source of weather on planet Earth. And that El Nino effect is what sort of started me doing. And I started hearing about it from these climate change models. And I said, that sounds like bullshit. And I did it. I modeled it. I went, whoa, wow, man, look at that. Because there's a point where the currents in the south go round and round and round, and they stay down there. The currents in the north go round and round and round, and probably the other way around. Anyway, they're going counterclockwise in the north and clockwise in the south, and they don't cross the equator as a general rule. The air currents can a little bit, right? Because they're a little less, they're more subject to the solar input than water. Water's like a temperature regulator thing, and that's what the oceans do. They regulate the temperatures on the land. And they do that by having the polar ice at either pole. And underneath that ice, the ice, thin layer, the rest is water, right? So we're looking at the ice here, and right under that ice, there's a thin layer of water that is 3 degrees above 0 Celsius. And that's why water floats. That's where water is the most dense. If that temperature goes up 2 degrees to 5 degrees Celsius, the ice sinks. And when it's below the water, it sublimates into water kind of all at once. Maybe you've seen an ice cube on a hot sidewalk melt. Or a glob of ice cream, right? Your kid drops a glob of ice cream, and you can watch it sitting there, and then all of a sudden it just kind of goes, bloop, turns into a liquid. And that's what's going to happen. If not this solar maximum, and the south has longer summers than the north does, and that's why the El Nino current, which jumps the pole, and jumps the equator, is so important, right? Because that solar maximum in the south is what drives a lot of the weather in the north because of that influx of hot water coming up from the south. That's the El Nino current. And it spreads around, of course, in the North Pacific. But it gets under the ice, and the ice begins to melt on the sides and falls off faster. But that's not what does it. That's not what does it, right? It's not going to fall off a piece at a time. What's going to happen is that very very necessary equilibrium underneath of the ice with that 3 degrees Celsius water goes away. And the ice sublimates into water. And all of a sudden, we don't have all that ice holding all that water and the poles, and it moves towards the equator because the planet's going round and round and round, and the moon's pulling it, of course, the tides, and all that water. What that's going to do is raise the water level a lot. It's going to inundate the coasts and drown every city in the world, just about. Very few cities are above 1,000 meters above sea level. The city of Phoenix, where I live, is 950 meters, I think, is the official thing. And I think I'm right at 1,000 meters where I live, in the Sierra Estrella foothills. And that's likely to be beachfront property in about 2 years. That's how long. There was indicators at the end of the climate model things that I ran, and I ran it like hundreds of times, not just once or twice. And so did these other guys, right? And I read that not like in Scientific American or a popular science thing. Read it in Science magazine published by the American Association for the Advancement of Science, and it came with the math and their methodologies for climate modeling. Science papers, real science papers that people present for whatever purposes. They tell you publish or die if you're going to be a professor at a university. And so they publish these things and do their work to hold their jobs, for one thing, but also because, like me, they're curious. And they want other people to know, and so we publish our work not just for peer review, but for other people to get that information. That's why we did it. So and their models, the two that I read before my own, agreed. And there's this at the end of the process, it starts fluctuating really faster and faster, and you get worse and worse and worse storms. And like this past year, we had the hot weather into November here in Phoenix, Arizona. I was running my air conditioning the second week in November. That is a first in the 35 years I've lived here. It is getting worse. And what's going to happen is an opposite of that, a colder winter, or summer, spring, winter and spring, in the southern hemisphere. And indeed it was like 18 degrees Celsius on the solstice, summer solstice in Lightning Ridge, Australia. And this is supposed to be desert down there, right? 18 degrees is like less than room temperature, man. On the solar maximum day, on the their summer solstice, 21st of December. But by the end of this summer, as they go into their fall, you're going to see maximum temperatures reaching 50 and 55 degrees, where normally it's never over 40 degrees. It gets 55 degrees here where I live. Once it's gotten that hot before, and it got that hot 51 degrees this past year, this past summer. And we're going to see temperatures up around 55. That's more than half the boiling point of water. So the question arises, I mean, do you have a surfboard? And if you do, if you don't, how long can you tread water?